Cool, thank you. Now I will start to get my Awkward setup and talk about the basics of DataLad with screencast. There is code to follow along at the DataLad handbook. If you obtain the slides or click the link in the shared notes, then you can get to this page here at the DataLad handbook, where there are copy and paste code snippets that you could use to paste them into your own terminal. And there's also a little bit of background explanation, which I'm trying to incorporate into what I'm saying, and links to chapters in the DataLad handbook. If you want to find this from the main page of the DataLad handbook, then it's quite simple. You just have to go all the way to the end, and then there's an introduction to DataLad at the MPI Berlin. Alrighty. Okay, so as a prerequisite, if you want to code along, then you will need to have DataLad installed and configured. So if you type something like this into your terminal, then it should return a DataLad with a version string, and that should be a fairly recent one. If you've installed it from, let's say, pip or other package manager, then it should say 0.13.5, which is the most recent release. And you should also have a configured Git identity. So if you would run this command, git config list, to list all of the configurations Git knows about you, then it should have a username and an email address that is associated with you. If that is not the case, then this is, and it's also in the DataLad handbook, how you would add this configuration for your local computer. And that's probably only the case for people that haven't used Git before. Okay, so one thing that I mentioned already is that DataLad is a command line tool and it has a Python API. So you can use DataLad either in its command line API, where here, for example, I'm showcasing DataLad create command, but you can also use the same command in its Python API, where you would, for example, do an import of the Python module DataLad API SDL, and then have access to all of the DataLad commands as methods of what you have imported. But if you don't use Python, which is completely fine, then you can use it also in most other programming languages, just via system call. So here's an example of how you can use it in R with the system call, and then you can type the command line call that you would commonly use in the command line. Now let's start. I've already mentioned that DataLad datasets are DataLad's core data structure, and that a dataset is just any directory on your computer that you instruct DataLad to manage. And I've told you that they can be created from scratch or from existing ones. They can also be installed from remote sources, and that they can also be nested and linked. But let's start by actually looking into how a dataset can be created. And here's an example of how I do this. I'm using the DataLad create command to create a new dataset on my computer. If I execute this command, then DataLad will create a new directory that is called my analysis, wherever I'm currently running this command. One thing that I have added to this command is a configuration option with the -c flag that is called Yoda. I will have to only later get into the details of what this does, but it applies a set of useful configurations that are adapted to the use cases of data analysis, and it applies also some useful pre-structuring to the data set that I have just created. So if I take a look into the analysis data set, in that I change directories, so cd into it from my terminal, and then take a look at the directory structure that I find inside of this with tree. And that's a command that Mac OS and Windows users may not have, so you would need to find an alternative on how to view that. You can see that this is a directory on my computer that is already pre-populated with some things that we regard as useful to have in a data analysis, namely a code directory and some README files that are pre-populated with some placeholders to encourage you to write documentation and README files for your data analysis project. Now, if I take a little deeper look into the dataset by not only listing the contents that are seen to the naked eye, but listing all contents with the -a flag that also shows hidden files, I can find a couple of so-called dot directories or dot files, .datalad, .git, .attributes. Those are hidden files for a reason. They shouldn't be tampered with unless you know what you're doing. But those files are an indication that there are version control tools working in the background in this repository. And that's an indication that we can perform version control operations here in this dataset. And I'm going to show you how this is done. So the first thing that I'm going to do is I'm going to make a change to an existing file in this dataset to show you how I can see those changes and track them. What I'm doing here is a little bit convoluted because I use the command line to delete the placeholders in the README file. I do this by just echoing an empty space into this README file. And that's not the common way that I would delete contents, but this way I can do it in a terminal. You can also just take an editor and delete all of the contents of that file. If I now want to query the dataset, what it thinks of about what has just happened, then I can use a command that is very similar to the git status command that Lennart has shown in the concept section, which is called DataLad status. DataLad status reports on the current state of the dataset. And since I have modified a file that was placed into version control with DataLad and then changed this file shows up as being modified. And I can take an even closer look into the precise nature of the change if I'm using the git diff tool, which Lennart has also shown, I think, to actually highlight everything that I've replaced and everything that I have put into the file. So you can see those red highlights with a minus at the beginning of the line, and those are the lines in the README that I've deleted, and the plus, that's a line that I have added, which is just an empty space. I will do the exact same thing to the other README file that is placed in the code directory, so that I now have two changes. They are pretty much identical. They are just deletions of the placeholders in the README files. And if I would say that's a fantastic change in my dataset that I really want to save and have in my revision history, then there's one a command that I can do in order to save these changes, which is the datalad save command. And datalad save is a command that takes the current state of the dataset and will record it as is to the dataset history. And the current state includes all files that are in the repository but yet untracked, and all modifications that are done to files that are not yet tracked. What I'm also attaching to this save command is a -m option, which is short for --message, which is an option that lets me define or attach a short, concise summary of what I have done, which is the commit message that I will attach to those changes. If I execute this, then DataLad will record the changes that have been done to those files and save them into my dataset history. And now let me show you how I'm going to. So now I'm going to do another change in order to display an important construct here. I'm just opening up the README file in a text editor in my terminal, and I'm just going to add some contents. Let's say my first DataLad dataset, and I'm going to save that and close it. And here's what has changed so far. Cool. So that's nothing out of the ordinary. Just as we have seen, there's a change to a tracked file that now shows up as a modification. But what I'm going to show you now, because version control is so super easy, is what happens when I have a second change that is unrelated. So what I'm doing with this next command is I'm going to download with the wget command a internet comic from this URL. If I execute this, then wget will place a new file into my dataset And if I run DataLad status on the current state of the dataset, then you can see that I have an untracked file, a PNG, and a modified file, the readme.md file. Now, one important thing to note is that DataLad saves the complete state of the dataset. And in order to create a nice and clean revision history, a nice and clean dataset history in my dataset, I want to make sure that I only save those changes into a save that belong together. Because my main motivation to have a nicely set up revision history is to have a clean set of steps that I have taken, and also the possibility to revert singular changes I have done to my dataset without affecting unrelated changes. And here is how I would do this. I have two changes in my dataset, and if I want to use DataLad's core API, DataLad save, then I'm simply attaching a path to the precise file that I want to save. If I execute this, DataLad will not save the complete state of the dataset, but it will only save the modifications of the file that I have specified in the path, and the next DataLad save will take care of saving the remaining changes. In this case, it's the compiling PNG, which I can then associate with a fitting commit message as shown here. So what you, just as a quick summary of what I've just shown you, what you've seen here is that DataLad dataset is a directory with version control capabilities, and it is a joint Git and Git Annex repository because we have those tools working in the background for us in order to provide version control capabilities. And version control is nice because I was able to keep things organized and to keep track of the changes that I have done to the README and to the dataset as a whole. And I can now revert changes or go back to previous states. And I'm going to show you quickly how that is done. But before that, just as a reminder or just as a summary, with DataLad, version control boils down to two things, datasets and files. So once you have a dataset that you have created with DataLad create or installed, then you can just place files in there or modify existing files in there and then do a DataLad save in order to save those changes. Nevertheless, you can still use Git commands if you're more comfortable with using those, and Git Annex commands with using those. But DataLad save is the one that is in DataLad's core API. And because version control is so easy, version control is very easy because every file that you put into this dataset can then be really easily version controlled regardless of its size with the same command. So procedurally, even if you have never used Git, if you use a DataLad dataset, then you can use a single command or two commands, create and save, and then maybe status, in order to get from no version control to version control. And because it's so simple, you can follow best practices quite easily, which boil down to saving meaningful units of change, so only those that belong together, and attaching helpful commit messages to what you're doing. And although I've shown it here only with very small files, this means that you can also version control your data. So let's take Lennart. He has recently acquired an fMRI study, and now he can take all of his large neuroimaging data, which are gigabytes per file, add them into a dataset, and then just do a DataLad save of all of his files, and they are safely version controlled in his dataset. And that is something for those people that don't know Git, that Git isn't capable of doing because it doesn't handle files that are too large very well, and it also doesn't handle binary files very well. And in a second, I will go a little bit deeper into the reasons of why that works and how that works. But first of all, I want to showcase some of the features that version control has. So one thing is that you now have a history of what has happened in your dataset, and all of the files have this history attached to them. So I can now use a command such as git log on a particular file to find out everything that has happened to this file during its existence. And I'm going to take this moment in order to show people that are unfamiliar with Git what we're seeing here. Because it's an unfamiliar view for those people that haven't used Git, but it's also a view that is occasionally to get used to if you do it regularly. So what you can see here is a revision history, and you can probably see those commit messages that we have applied here. So one of those blocks that I have just highlighted, that's a single save and one entry in the revision history of the dataset, and an entry that is associated with this README file. So you can see that such an entry consists of a bit of information. For one, there's a human readable commit message, and I make use of that commit message because I can now identify what has been happening at this change, so I have an incentive to do an informative commit message. You can also see that there's a date and an author attached to this commit, and that's where the Git configuration of your email and username actually came into play. And then you have something that is called a char sum. This is this weird 40-character string right here. And this is a sequence of characters that uniquely identifies every single commit in your history and every single version of a file or a data set. And that is a useful thing to do, because what I can now do is I can interact with this history. So something I am capable of doing with a Git history, and people that have used Git are familiar with this, but I'm going to show it just for the record and for people that have never done this. I can, for example, take a bit of this commit hash and give it to the git checkout command in order to revisit the state of the dataset at this commit. So if I take a look at the README that has existed at this state of the dataset, you can see that this is the state of the README where I had deleted everything. And I can then go back to the most recent state by checking out the branch, which is by default called master, that I was previously on at the most recent point. And if I now take a look into the README, then I can see, oh, the contents that I have added with the most recent commit, they are back again. And although this was only a very brief and quite basic exploration of this Git history, you can go really fancy. And what this tries to demonstrate is that if you do this revision tracking, then whatever you have ever placed and saved in a file that is version controlled is never really lost. You can bring it back to life, or you can just take a look at it if it's useful for you later. Okay. Now, one thing that DataLad adds to what Git can do is that it has the capability of recording provenance. And if you have, for example, ever saved a PDF onto your hard drive and then forgot where you got it from when you wanted to actually send a link to someone else, then you know how important it can be to have a reference or a record of where that file actually came from. And here's where the term digital provenance comes into play, and we'll see that throughout this workshop. Digital provenance is defined as the tools and processes used to create a digital file, the responsible entity, and when and where the process events occurred. And Git already tracks a lot of digital provenance in the form of these commit entries, but DataLad adds a couple more provenance entries to them. And the first one that we'll see is that we can record where a file comes from if we obtain it from, let's say, a web source. And here's where I'm going to demonstrate what is called the DataLad download URL. And I'm just going to hide a little Easter egg in my dataset by downloading a comic and then saving it into the dataset under the name .easteregg, so that it's a hidden file that is a comic that people can maybe discover. And you can see that the DataLad download URL also takes a commit message where I'm summarizing what I'm doing. Then it takes a path onto where something that should be downloaded needs to be saved, and it takes a URL on where I need to download something from. And when I execute this command, DataLad will download the comic, it will save where its origin is, and it will register, or it will save everything under the commit message that I have just given. And if I now open this Easter egg with xtg open, that is a Unix command or a Linux command that uses whatever tool is registered to open a file. If you're on Windows, that won't work there. You would need to use start, as far as I know. But here's the comic. Okay, and in a couple of minutes, you will see where the provenance of the original location of where that file came from really becomes very, very useful. But before that, I want to give you a short summary of how local version control works with DataLad. So DataLad creates an empty dataset. And then there are those procedures, for example, Yoda and also text-to-git, which you will see later, that are useful, even though you don't yet know why, but I will get to that. Now, each dataset has a history that is allowing it to track files and their modifications. And there are tools, for example, git log, and also tools that have a nicer visual interface, for example, tick, that can explore this history. If you want to save a dataset state, then you can use DataLad save. And if you apply a concise commit message to summarize the change, then you can be very helpful to future you and others to create a nice and readable commit history. DataLad download URL obtains web contents and records their origin, and then also saves the change. And DataLad status, just like Git status, reports the current state of the dataset. And you should make sure, just as a best practice, to have a clean dataset. That means no modifications and no unchecked files, because then you can be sure that you've never lost anything, or you don't risk losing something by accidentally deleting it, for example. And with a couple of commands, someone who has never used version control with DataLad can get from this state to this state. That means very neat and clean and simple version control routine. However, version control is only one aspect of data management, and I'm going to quickly go to the next, unless there are questions at this point about version control with DataLad. So if you would go back to your phones and give me a hint on whether you have a question, then I have a chance of maybe answering it. And maybe you're also answering or asking questions in the chat. Then. Okay,
yes, maybe just to summarize what happened in the chat. So Andre asked something about where files, where the files go that you save into the data set. So if they go to Git or Git Annex, and for example, how this interacts with the Git ignore file. But I already told him that you will cover this in a bit.
Oh, thank you so much. Okay.
And maybe I have a question, actually. So I also used DataLad save on just a regular Git repo that wasn't a DataLad dataset yet. And that also works, right? I mean, I think if I remember correctly, it worked.
I think so, yes. I assume so.
Yeah, because in a way, I mean, it seemed logical to me, because in a way, if a DataLad save subsumes both the git add and the git commit command in one command, essentially, then it should do the same thing, even on a Git repo that is not a DataLad dataset yet.
Yeah, I think so. If I'm mistaken in that, then Michael or Benjamin can probably intervene in the chat.
Yeah,
okay.
They just answered. It is meant to work.
Okay, cool. So now I'm going to continue and talk about consuming datasets. So you've seen that creating a dataset is perfectly possible, but you can also clone datasets, install them, and then have access to their contents. And I'm going to show you how that is done by going briefly out of this dataset that I've created and instead cloning another dataset. This is a somewhat domain-agnostic dataset, which is just a collection of machine learning books. You can see that the DataLad clone command is really fast. And if I go and take a look into the machine learning books, then I can see that there are quite a number of books inside of them. So while PDFs are not usually that large, it was a remarkable fast pace of downloading. Now, something that is intriguing about DataLad datasets that one has to know in order to not be confused is that they are incredibly small. So if I take the du command, disk usage, and display the disk usage of this directory in human readable sizes, that's what the sh flag does, then you can see that it's only a couple of kilobytes, and that's definitely not enough to cover the size of all of those PDFs. And here I have summarized that also in this GIF. So if I have a neuroimaging dataset that is super quickly downloaded, then I have all of these files, but they are super small. And the reason for that is that upon installation, only very small files and what I would refer to as metadata about file availability and file names are retrieved. And that means that this dataset that I've just cloned, or a gigantic dataset with terabytes of data, is super lean. And the reason for that is that, may sound funny, is that there's no file content yet available directly after cloning. So here's another example. When I'm cloning the study forest dataset, the neuroimaging dataset, then after cloning it's only 18 megabytes. But file contents can be retrieved on demand, and that happens with a DataLad get command. And I'm going to show you how this works in a second. But before, I'm going to show you how you can actually find out how much content is present in a dataset. So if I use the DataLad status command with the annex flag, then I get a report on how much data is there actually to retrieve, or how much data I have basically access to. And you can see here, there is a little bit more than 60 megabytes of PDFs that I have access to in this data set now. And now if I want to have one particular book or a set of books, then I can use DataLad get to retrieve the content of this file on demand. And you can get a complete set of files. You can use globbing, as I did here, to retrieve every file that starts with a D. You can get directories, so you can be really flexible with those calls. But importantly, you can see here that the content of those files is now actually downloaded, and that takes a considerable amount of time longer than the cloning, because now only the content has been retrieved. This is a really important and nice feature of DataLad that I frequently use, because this allows you to have more access to data on your computer than you have disk space. Here's an example of some of the larger datasets that we use from day to day in our institute in neuroimaging. One is the Enhanced Nathan Klein Institute dataset that takes up on our cluster 1.5 terabytes. But if I clone it on my computer, then its full size is only 1.5 gigabytes. And I think that's the second largest dataset that we currently manage. That's a collection of the Human Connectome Project dataset that entails 80 terabytes almost and more than 15 million files. If I download this one in full, or if I clone it in full, then it takes up considerable amount of space, almost 50 gigs. But that's just a fraction of the 80 terabytes. And that is useful because frequently, at least in my analysis, I don't need all of the data. So I can here just pick whatever I need and only use that disk space. And also, I don't always need to have the data available. And actually, on my computer, which has a mid-sized hard drive, 500 gigs, I think I have access to more than 200 terabytes of data with this mechanism. Now,
Adina?
Yes?
Maybe just to quickly chime in here, kind of to give this perspective from my user experience when I first started with DataLad, like, I think it's really important to emphasize this concept of these lean data sets, and that actual file content might not be available, because it was, I remember it was also very confusing for me at first that there seems to be files when you look at them in your file browser, but you can't actually open the content. And this might also feel frustrating at first, because you think the file is actually there, but it's actually not. And but then once you learn that you can just flexibly get all the content you need, it's really an amazing feature. I mean, I don't have a particularly large hard drive, and like this feature to flexibly drop stuff and then get stuff I need really helped me in many situations.
Yeah, speaking of dropping, I'll continuous dropping. I noticed that I'm always so slow in the beginning. I need to speed up a little bit. So not only can you get things on demand, but you can also drop the stuff that you don't need anymore. So if you're done with an analysis, for example, then you can use DataLad drop to drop the file content to free up the disk space again. So here you can see me doing that on one file, and that is dropped. And that is a feature that, for example, allows disk space-aware computations that become very relevant, especially if you use large-scale data. Some workflow that we, for example, often use is we install input data into an analysis data set. It's really lean. Then we get only the data that we need and compute the results. And then we drop the input data as soon as it's not necessary anymore, while it is still linked in a precise version, and only the file content isn't there yet. And later I'm going to show you how you can also drop all results that are potentially automatically recomputable in order to save disk space. And there's one way of doing it, for example, directly in the scripts, where your script starts with the DataLad get and ends with the DataLad drop of the input data. Okay. And one thing that I now foreshadowed in when I said that we want to not only show workflows and what works and how it works, but we also wanted to provide some in-depth explanations, because I think that's an intriguing mechanism that warrants some additional explanation. And that is where I need to take you into the depth of Git versus Git annex, and I'm apologizing for that, but I hope that it contributes to a better understanding of what DataLad does. So one thing that you need to be aware of is that data in datasets is stored in one of two places, either in Git or in Git annex. And if you create a new dataset without any configuration, by default everything is annexed. That means that Git annex handles the data and actually stores it in a hidden place, so to say. Now, the reason for the separation of Git versus Git annex is that Git cannot cope with large file content. So Git handles small files well, text and code, and it also does particularly well with text-based files that are non-binary. So anything like an Excel file is bad. A TSV file is good because a TSV file is text-based. A Word doc is bad, that's a binary. A text file is very good. Git annex can handle all types of files and all sizes of files well, but it handles them differently than Git because it stores them in a dataset annex, which isn't necessarily published to the same place as your Git history. This makes it the only way of version controlling large files and a cool way of exercising access control for private files, whereas everything that is stored in Git is shared whenever you, let's say, install a dataset right away. So these are the small files and the file availability metadata, the text, the file names and so forth that are available right after cloning. So that's what's in Git. And storing files in Git, that is useful for small files, non-binary files, files that need to be frequently modified. I'm going to have an insight on why that is later or in the next slide, and files that need to be readily available once somebody clones your datasets, for example, data usage agreements or readme files. And when something is put into an annex, then what happens is that Git annex produces a content identity hash in order to precisely identify the content of a file. Only that content identity information is put into Git, while the file content is managed with Git annex, and transport logistics exists to then transfer the data wherever you want it to have. Now, so as a visual summary here, the dataset is basically separated into two parts, Git and Git annex, that DataLad combines into a smoothly combined interface, so to say. And Git annex importantly handles files differently, and there are two main aspects where you can see that. For one, all of the annexed files, those are the files where you actually need to DataLad get the file contents after you've cloned the repository. So annexed contents need to be retrieved on demand and are not readily available there. And files that are stored in Git Annex, and I'm going to show you that at the middle of the demonstration, they are not modifiable because Git Annex write protects them. That sounds severe, but it's actually something that can be prevented or circumvented and worked with really well. But it's something that is a frequent source of confusion. If you accidentally annex a file, then Annex will not immediately make that file writable for you. And I'm going to demonstrate that in a short while. But those are the important things to know about the difference in Git versus Git Annex on how they handle files. Now, importantly, when you share a dataset, which we will discuss in the last section in the afternoon, then the place where you store your dataset may not have support for hosting also your data, because on GitHub, for example, you can't push gigabytes of data. And this is where Git Annex comes into play, because Git Annex has the transport logistics to put your data somewhere else to the service that you're using anyway, link the location where the data is stored to the dataset, and then make the data retrievable via DataLad get in the background without anyone who consumes your dataset actually caring on where they are retrieving those files from. So it looks like those files live on GitHub when I clone the dataset, but they actually come from a place that actually can store the large data. Now, one thing that you as a user are probably interested in is deciding whether files are stored in Git and Git Annex, and there are many ways to do it. One is via those run procedures that I have shown you with the configuration option Yoda. And there are other ones, for example, let's say text to Git. Text to Git makes sure that every text file is placed in Git and not Git Annex, whereas Yoda makes sure that the README files are placed in Git and not Git Annex, and everything that's in code. You can also create those run procedures. There's a tutorial on how to do this, and it's fairly easy. You can write rules where you just specify a directory or a file name, or let's say every file that's larger than 20 kilobytes or something that you can place in your dataset, or you can do it on a per command basis, for example, when you add the to Git option to DataLad save. Okay. I have shown you this already, and one thing that I want to show you too is that Git Annex protects your files. So if I go back into my terminal and go back into the analysis, my analysis dataset, you've seen that I have dropped a PDF beforehand, and I can now drop also the Easter egg PNG that I have placed into this file. But if I want to drop a file where no record of another origin is recorded, so where I don't have additional digital provenance attached. Remember, this file was obtained via a wget command. If I drop this file, then Git Annex will, or DataLad will warn you that the drop doesn't work, because Git Annex prevents you from accidentally losing data where you can't reobtain it. You can configure that behavior, but anything where DataLad doesn't know where to retrieve it from, you can only drop when you use the --no check option or a configuration in order to really tell those tools that, yes, that's a file that I want to get rid of. Now, I'm going to quickly show you what Lennart already mentioned, how weird it is if file content isn't there, but there is a file name. So remember, I dropped this PNG. If I now attempt to open it, then tools usually error out really weirdly because they don't know how to handle this. If I then get the file again and note how now the recorded origin from web, so from the XKCD website, is queried again to retrieve the content, then I can open the file again with a tool of my choice. Alrighty. Okay, done that. So now I'm going to show you how nesting works, because you've seen how I've created a dataset and how I've cloned a dataset, and now I want to show you how you can nest datasets into each other. And I'm going to do this with a very similar command to what I've already run, which is a DataLad clone command, but I'm, in this case, preparing a data analysis that I want to showcase here. And in order to do a data analysis, I need input data. And I want to link the input data as a subdata set into my analysis data set so that I have a registered unit that is in a precise version. What I'm doing, therefore, is a DataLad clone of this URL where there's some data, and I'm attaching the -d, that's short for dataset, option to point to the root of the current dataset. And that means just clone this dataset and register it as a subdata set to the current dataset. And I also apply a path here because I want to save it under a specific path that is called input. So if I execute this, then DataLad will clone the dataset from GitHub and store it in a new directory called input. So now I can say here there is input, and in there's not much. It's a short demo. But there's a dataset, and I can now use the DataLad subdatasets command to list it. Now, importantly, input is a dataset that has its own revision history, and that one is short, but it's completely independent of the analysis dataset that I've created. So here you can see that this is the very short history that this dataset has had in its life, and by cloning it as a subdataset, I still have access to all of this history, even though it's inside of this analysis dataset. There are two advantages of nesting things instead of just saving input data, let's say, to a dataset. For one, it overcomes scaling issues. So if we are version controlling 15 million files, that's something that Git would struggle with. But by nesting datasets, it's no problem at all to version control an extraordinary amount of files. And DataLad adds recursive capabilities so that I can use a hierarchy of datasets basically as a monorepo that I can apply all of the commands that I would apply to a single dataset throughout the history of datasets, just as if it was one repository. But more importantly, this concept modularizes research components, and that makes it more transparent. It makes the, let's say, input data more reusable, and I can apply access management on a per dataset basis if I want to. Now, what has been registered when I did the DataLad clone command to clone a subdataset, I, for one, know where the subdataset came from, but I also know which version of the subdataset is installed. So the record that has been created in my super dataset is a path to where this dataset lies in my super dataset. It's a URL to where it originally came from, and importantly, it has this what is called a sub-project commit, which just points to the most recent commit and is thus able to precisely identify which version of a subdataset is used in a particular subdataset. So as a quick summary, at this point, DataLad clone installs a dataset, and they can be installed on their own, just from a path, a URL, or with an optional path where it should be installed. Datasets can also be installed as subdatasets if I apply the dataset option. Importantly, when I clone a dataset, there are only those files that are placed in Git present after an install. And to retrieve actual file contents of all those files that are annexed, you need DataLad get to download the content on demand. Datasets preserve their history, so if you clone a dataset, then you have its entire evolution ready to go. And if you do it in a super sub-dataset fashion, then the super dataset records only the version state of the history, but nothing of the individual dataset's history. Okay, quick question round of whether there are questions at this point. Not.
So,
Yes.
there was one question by Andre about using different types of remotes, for example, Gin remote, and if that's different from hosting like for example, code and then the actual annex content. But I mean, we'll get to publishing later, right?
Yeah, if Andre can wait a little bit longer, then it would make things easier if we can get to that when we have planned to.
Yeah. Oh, good, Andre. You don't need to be patient. It's a very exciting topic, so we like to see that people get excited about it.
Okay. So now I'm going to show you the basics of reproducible data analysis with DataLad, because generally your past self is definitely the worst collaborator because you usually don't reply to emails of your future self. For this, I'm going to quickly skim through something that I'm going to repeat in the section on reproducible science, which are a set of organizational principles that are very useful and easily applied with DataLad that help to make data analysis projects intuitively structured and clear. And one of those principles is that everything should be kept very clean and modular. So if you have an analysis, then it's good practice to keep that one as a super data set, but every component that's relevant and a standalone unit should be a sub-data set. So if you're using several input data, then you have several sub-data sets that consist of this input data registered to the super data set. This allows you to not touch or modify the raw data, because by modifying raw data, you for one make it very difficult for others who take a look at your data set later to figure out which is raw data, which is derived data. And it also keeps the raw data reusable and useful for another analysis. So when doing a modular setup, make sure that the outputs that you produce on your input data are actually stored outside of input data sets, right in your analysis data set where you probably also host your code. So here are two views on that. One is this kind of hierarchy through time where you go from raw data to bits to fMRI prep to analysis to paper. And here's the view of that in a single data set, for example, the analysis where you have a code directory and maybe also a singularity recipe. But then the input data is a standalone component, and or maybe even several. And the outputs, they are saved into the actual analysis data set. Now, the next thing that you need to do in order to create a data analysis that is intuitive and easy to reproduce is to make as much records of everything as you can. So you should record where you got something from, where it's now, what you did to it. And DataLad provides the features that allow you to do this. So you can link with the datasets and the sub-datasets where data comes from. So what is the origin? You can collect and store the provenance of the contents of your dataset, and you can document which script produced which output from which data in which software environment. And I'm going to show you how that is done right now. So what I'm going to showcase here as a quick example is a go-to tutorial for any introductory machine learning course, a classification analysis on the iris flower dataset. That's just the CSV file that consists of sepal and petal length of 3 species of iris flowers. And what we're doing is we use a clustering algorithm to predict which flower it's going to be based on the features that are measured. And for this, I'm going to write a quick script into the terminal in order to save it. That's a little bit of convolution, but it still allows me to remote control this terminal and gives me the time to add an important rule that I've forgotten to tell you for intuitively structured data analysis. It is really important to keep datasets self-contained so that they are a portable unit that does not only can live on your computer, but also on your cluster or on a supercomputer or on your friend's laptop. And the main way that you do this is that whenever you compute anything, you don't hard code absolute paths into your scripts, but you keep everything relative and self-contained so that the super data set references everything that is underneath it as relative paths. And I can show you how this is done, for example, here, where we reference the data in the subdata set, not with an absolute path that would hard code features of my personal file system that are not replicable probably on any other computer into the code, but I use a relative path so that I can send this data set to Lennart, and he will be able to find the CSV file exactly where I left it, and the path resolves because it's a self-contained unit. Now, one thing that I also wanted to show you here, it's going to be super superfluous, but I wanted to just include it to give you an idea of how Python API call of DataLad looks like. Prior to anything being computed, the input data is actually getted. And what this script does is nothing fancy. It reads in a CSV file, it plots the relationships that are in the CSV file, and it saves a prediction on a test set into another CSV file. And in the section on writing a reproducible paper, we're going to reuse this analysis for this. So now that I have added this blob of text into a file on my dataset, I can run datalad status, and there's a new untracked script .py file in my dataset that I can save with the datalad save command. And here you can see that I'm also applying a version tag, which is the equivalent of a git tag, and just one other way of attaching some sort of identifier to a commit message or to a commit entry in the history. And nothing spectacular happens. It's just save the script when I do this. And if I now do a datalad status, it's clean. Nothing to save, working tree clean. And that's important for the next command that I'm running, which is the datalad run command. And before I use this command, I'm going to show you a visual explanation of what this command does. Datalad run basically takes a command. In this case, it is this invocation Python 3 code script.py, which does nothing but executing the script that I have just added to the dataset. And it executes this command, and whatever happens as a result of this computation is saved under the human readable commit message that the command takes. Datalad run has also some optional flags. One is input. Anything that you supply as input is retrieved via datalad get before you run the command. So if you specify all of the inputs that an analysis has, and you can do this in a very broad manner by, for example, just pointing to a directory or a complete data set or a glob, then you can make sure that all of the inputs are actually retrieved prior to running something. And then there's the output flag, and the output flag takes care of making annexed files, should they be there, modifiable, so that if a computation is redone, the result can potentially be updated. And I'm going to show you in a bit of time how this actually works a little bit better. So if I execute this script now, datalad will take the command, run it, and then associate the results of this computation. In this case, I knew them beforehand and were able to supply them to output specifically, but I could also just use a glob, a directory, or whatever. And it saved them into the dataset under what is called a run record. And this is how a run record looks like. It's not the most human readable thing to have. So it's this machine readable structure that associates all of the relevant information, but it also has this commit message. And if I would take a look with tick into the history, then I could also see precisely which files have been created with it. And now I want to show you exactly how this can be really, really useful. By just cloning the so I have created this dataset beforehand and have published it to GitHub. And now I'm going to show you how this run record can be used by cloning this published dataset. Let's pretend I'm just a collaborator of myself and I'm now sharing this data analysis with me. If I take a look into this analysis clone here, and then do what is called a rerun of the commit that has produced the run record. So in this case, I already know which commit hash it is because I've peeked, but I can just take a look at the dataset history, identify the SHA sum of the commit, and plug it into DataLad rerun. Then DataLad can read the machine-readable record, and it makes sure that all of the inputs that are specified are retrieved, that all of the outputs that may be there are unlocked so that they can be updated, and it recomputes the exact same thing without me having to hold myself, my past self at gunpoint to find out how I have done anything. And the git log then makes a record of everything that has been done to the files that were created. Now, thing is, that's already quite nice. It's a very simple concept that has a lot of advantages, but it essentially doesn't go far enough, because it's nice to have this automatic recomputation, and it's no surprise that it works if I do it again on my own computer. But if you have a script and try to rerun it on a different computer, then that may fail because it may be run with a different software environment. So if I'm sharing this dataset with Lennart and he doesn't have the Python packages installed that I used, then that will just fail, and that's very sad. But datasets luckily can store and share software environments in the form of Docker or Singularity containers, and then not only do a run like the one that I've shown you, but actually execute a command or a script inside of a software container in order to capture the software container as additional provenance. And that is achieved with the DataLad extension, the Python packages DataLad containers, and the command DataLad containers run, which is just an extension of DataLad run that also includes a software environment. And if I want to do this, the first thing that I'm doing is I'm adding a software container, and we'll go into the details of that in the first afternoon session. You can see here that I'm adding a software container from Singularity Hub, and I'm registering it under the name software, very, very creative, into my dataset. And what you can see here now is that DataLad retrieves the container image that is built on Singularity Hub and stores it inside of my dataset. And also, because I'm adding it from a URL, it registers this public URL into the dataset. And if I want to recreate this analysis then in a software environment that I can share with others, I'm using a almost similar command. So I'm exchanging DataLad run with DataLad containers run, and I'm adding the additional specification of the container name that I'm using, because I can have several containers in a dataset if I want to, and then just re-execute it. And in this case, the output is not going to be spectacularly different, but I now have a dataset record and a dataset that includes a complete record of everything that's necessary in order to reproduce a result. And that's quite nice. And that's not only nice for somebody I share this dataset with, it's also nice for me if I ever go to a new computer, or if I ever forget how something is done, or if I'm just being lazy. So one thing that I frequently do, for example, just as a quick example, is I'm using DataLad to get rid of my short-term memory. Because if I now just edit the script a little bit, let's say, because I'm not really happy with the color scheme that I have. And that could be any kind of change that I would do to a script file. I could also add new functions or whatever. I'm saving this, I'm exiting, I'm doing a DataLad status. Like this, it's modified. I can save this modification. Just briefly, I forgot the commit message. I'm very sorry, that was not best practice. But now I can do a DataLad rerun. I have remembered that the last run that I have attempted to do was not the last, but the second to last. So I can do, I think, this. And if I do this, then it will take the run record, take the updated script to just redo my computation, and I now have figure that has an updated color scheme instead of the color scheme beforehand. Cool. So as a quick summary for reproducible execution, DataLad run records a command and the impact that it has on the dataset. And whenever DataLad run command is ran, by default, all modifications to the dataset is saved. And that's plainly the reason why you need a clean dataset status, else it would associate untracked changes that existed beforehand to your dataset in conjunction with this script, which it will not do per default. So if you do it in an unclean dataset state, it will refuse to run. There are, however, options where you can still make it run and just define precisely which outputs you want to save and associate. Everything that's specified as input is retrieved prior to command execution. And if you have several inputs, then you just use several flags. And everything that is specified as output will be unlocked for modifications. And that's useful for everyone who reruns your command, so that files that changed during two different executions can actually be modified. Then there's DataLad containers run that comes from the DataLad container extension that can be used to capture the software environment as additional provenance. And that ensures that computations are run in the desired software setup. And there's support for Docker and Singularity containers at the moment. And DataLad rerun can then automatically re-execute a run record in the history later. And you can identify such a run record however you want with all the tools that basically Git provides. You can use a commit hash, you can do the head specification that I have done, you can use a tag, you can also use a range, you can be creative. Now, DataLad rerun is very helpful to spare others and yourself the short and long-term memory task, or equivalently the forensic skills to figure out how you performed an analysis. But importantly, it's also a digital and machine-readable provenance record. So it goes beyond the README description of what you have done, providing everyone that you share your dataset with and yourself the ability to recompute something automatically. And because all of the outputs are tracked with their content identity, regardless of whether they are stored in Git or Git Annex, you have a direct way to assess whether a rerun changed something in the results that it produced. Because if something changed, then it will actually do or create a commit in your dataset history. And in your history, you will be able to identify which file has changed. And if it's a non-binary file, you can even see precisely how it was changed. Or you can check out the first run version that it produced and compare it to the version that was produced with a rerun. And yes, that as an important note, if you do a run or a rerun and nothing in the dataset state changes, then the execution doesn't lead to a commit entry in the dataset history.
Adina?
Okay, yeah.
So maybe just one comment from my side. When I started to use this DataLad run command, Adina, could you briefly maybe turn off the audio? Because then there's this echo. Sorry.
Yeah, 1 second.
Thanks. Yeah, just from my experience, I think that when I started with the DataLad run command, admittedly, I found it a bit tricky to kind of get it right and like properly link like the input and the output and then specify the command properly. And I found it tempting, I have to say, in the beginning to just like execute my script as I would usually do and then just do a simple DataLad save afterwards. But I mean, like you nicely explained, it's really useful if you later want to figure out how a change in a file came actually about and how you actually execute a certain file to then have these run commands. And also, if you are lazy, then also this rerun command just comes in super handy, because the only thing you need to do is find out the last time you ran a certain DataLad command or the DataLad run command, provide the hash, and then you can just rerun it. And you don't need to think back and need to figure out how do I actually execute this script in the first place. And also one simple way that I tend to use, I don't know if it's best practice actually, but I just look in my file history and then figure out, like usually if, let's say I want to change a certain TSV file by running a Python script, then I can look at the history of this history of changes of this TSV file, and then usually the last change was the previous run command or the previous rerun command, and then I can just get the hash, do rerun, and update the script in this way. So it's a very useful command.
Thank you for that addition. Okay, if there are no other questions, then I will continue with demonstrating 2 additional things that I find helpful to know about how DataLad works. It's outside of this let's demonstrate a start-to-end workflow thing, but belongs more to the here is actually how this tool works section. Unlocking things, something that I want to draw attention to. So I've demonstrated that DataLad run unlocks everything that is specified as output, but you are also able to do this outside of a DataLad run call with the DataLad unlock command, and that makes files writable. And I'm going to show you how this feature of Annex with write protection actually works. So let's say I'm going to place a data file into version control by Annex. Now I have set up this dataset with the Yoda procedure. That means that everything in code is put into Git and everything in the README and changelog files is put into Git, but anything else will be annexed. So if I just do an echo of some numbers into an annexed into a file that I here call annexed files, and then do a DataLad save. Whoops, I have an American keyboard here. That's a bit annoying always. Annex a file. Then this file will not be stored in Git, but in Annex. And now I'm going to demonstrate what happens if I then try to write to this file. So if I just want to append another string of numbers to this file, then you will see something like a permission denied error that looks really troublesome if you're not used to seeing that. If I open it up with a text editor, then I get this worrisome warning of annexed file is unwritable. And that's something that would stress me out if I wouldn't know what that is. Now, the thing is that here on this slide, I'm demonstrating this. When I have an annexed file, then what this annexed file actually is, and this does not apply to Windows, but on any other system, this file is what is called a symlink. So that's what this structure here with this little arrow and this pointer, this is how a symlink is shown. And that means that the file contents that appear to be in my file actually lie in this very, very cryptic path that points to a hidden directory in Git, namely annex objects, which is the so-called annex object tree. And this is just the internal representation of where Git annex stores your files. And there's not much magic behind this. The cryptic characters here is just a representation of the content identity hash of your file contents so that they can be uniquely identified. Now, everything that's in this object tree is write protected so that you can't accidentally lose changes or lose a file or whatever. But that means that you get those permission denied errors when you try to edit them. And that's why it's useful to keep code and stuff that you frequently modify in Git so that you can just very comfortably always have add additions and then save them. But if you have something annexed and you want to do a modification, then what you need to do outside of a DataLad run command is a DataLad unlock command. If I do this, then the annexed file is unlocked. I can echo whatever I want to echo inside of the file. If I do a DataLad status, then I can see that it's now modified, and then I can do a DataLad save afterwards. Oops. Okay, and once it is saved, it is put back into the object tree where it's again write protected. So that's one thing of the peculiarities of working in datasets, but it can be circumvented by just placing that stuff that you want to have in Git into Git. And there are plenty of tutorials and rules and examples in the DataLad handbook to show you how that can be done. And it's also important that some tools, for example, MATLAB, don't like symlinks. So the tools that I frequently work with, like FSL, all those large neuroimaging tools, they can read symlinks just fine, but there are tools that don't like symlinks and then display cryptic error messages because they can't seem to follow these files. If you then unlock them prior to opening them, for example, with MATLAB, or doing the operation that you want to do in a DataLad run command prevents those errors, should you ever come across them. The next thing that I wanted to show you is how to remove a dataset, because that also can be relevant. And it's important. So frequently, the first dozen of datasets that I wanted to remove that went horribly wrong, because as mentioned before, the NX data is write protected. So whenever I remove a folder, I do it with the rm command to remove, and then supply rf to do it on a directory without checking. But if I try to do this on a dataset, then you get all of these messages that tell you, oh God, I can't remove this cryptic path that points to the object tree because that's the actual file that's write protected. And that's not really cool and ugly. And if that happens, if you accidentally ever do this, then what you need to do in order to get out of it is to, and that's a little bit ugly, but that's the workaround here, is you need to apply recursive write permissions. So the Unix chmod command, change mode, -r recursive plus W, apply write permissions to a dataset, makes everything writable and thus also removable. But the actual way to remove a dataset is to use DataLad remove. So if I go out of this dataset again, oops, and then do, oh, right, there's something that I missed. Obviously, so this is how you remove a dataset, but GitNX protects files, as you have seen with drop. And if you attempt to remove a file, then this will initially fail if there's any file inside of there that cannot be potentially re-retrieved. So let's say a result that only exists on your computer and where there's no, where no one knows that there's another copy of it. And then you will get such an error message. It's unsafe. You can't remove the dataset if you wanted to. And in that case, if you are really sure that you want to remove a dataset, then you can use the no check option to disable those checks to force a removal. And then you can also have datasets that have subdatasets. And if you want to remove a dataset with its installed subdatasets without doing anything particular, then it will also provide you a warning that this dataset has present subdatasets, and in order to remove dataset recursively, you can use the -r or recursive flag to apply the remove operation throughout the history. So in the case of when I want to, let's say, remove the analysis clone, I just supply it as the argument to the dataset option and say recursive and no check, because I'm really sure that I want to get rid of this dataset on my hard drive, and it's gone. Alrighty. And a complete overview of all of the common file system operations, should you ever want to know whether it's okay to rename a folder or a dataset or something, you can find in the DataLad handbook. And I'm here now only noting the things that I find most confusing as a beginner with DataLad to give you a heads up, but usually all common file system operations work just as in a normal directory on your computer. And I have...
Adina?
Yes.
Sorry, when you talked about a confusing beginner, I felt obliged to say something.
Yes, please.
So actually, this -d flag, I found it to be quite important to specify, especially if you have lots of different data sets and sub-data sets, to specify to which data set you want to apply a certain change, like, for example, a removal or a save command. So if you're in a super data set and you actually want to apply changes to a sub-data set, you can use this -d command and specify your sub-data set to then apply whatever you do to the sub-data set and not to the super data set. So that's what I found to be helpful, to just be mindful and use this -d argument to specify to which data set changes should be applied.
Yeah, thank you. Something has frozen. I need to reload this 1 second.
Maybe I can add something else then.
So everything is frozen, but if you can still hear me, that's actually okay. So I had prepared a full-blown, more complex analysis set up from start to end, but I took too much time talking. I'm very sorry about this. And I would suggest, instead of doing a 30-minute tour through a start to end input data creation, updating data, we go into lunch break, have a rest, digest what we've heard, and digest some nice food, and then come back to the afternoon session where we have a chance to take a look at the example maybe, and also the rest of the workshop contents.